All right, so day 4, we're going to recap transformations. We talked about it in Unit 1. This is something that we see in algebra and geometry and algebra 2, everywhere, all over math. So we really want to make sure we have this down. So we're going to talk about it again. So this was the unit where we talk about doing stuff in the inside, outside of functions, and how they transformed the functions. That's why they're called transformations. So here's a little chart we're going to make. If we add on the outside of a function, that is a shift. Oops. Okay, that is a shift up. Right, it takes the whole function, just shifts it up. And if we subtract on the outside of the function, it's going to shift everything down. Same with the shifts. Let's go inside real quick. So if we add inside the function, that's going to be a shift to the left. And if we subtract inside the function, that's going to be a shift to the right. Okay, so shift up, down, left, right. Okay, so that's just moving the whole function. Okay. Now, if we multiply by a value that is greater than 1 on the outside of function, that's going to be a vertical stretch. And if we multiply by a value that's between 0 and 1, so like a decimal, like a 0.5, a 0.3, a fraction, 1/3, something like that, that's going to be a vertical compression. If we do those things on the inside of the function, if we multiply by a value that's greater than 1 on the inside of the function, it's going to look very similar to a vertical stretch. It's going to look like stretching it vertically, but instead we're doing horizontally and we're compressing. So we're horizontally compressing. So that's a horizontal compression. And then again, by that decimal number or value between 0 and 1, that would be a horizontal stretch. Okay, so we'd like stretch the function out horizontally. If we multiply by a negative, if we do that on the outside, it's going to multiply all of those y values by a negative number, and essentially it's going to reflect over the x-axis. And if we do that on the inside of the function, we're going to reflect over the y-axis. Okay, so that is very similar to the chart we made in Unit 1. Here again, we have it to summarize that stuff. And I do just want to quickly talk about, so these transformations can be performed on any type of function, right? We've seen it done with quadratics. We've seen it done with other types of functions. I want to kind of talk about the difference between inside and outside of a function. So if I'm talking about, for example, if we're talking about, let's say, the functions we were just talking about last section. If I talk about the square root function, okay, this one's kind of a little bit easier to see because, you know, anything here, anything over there, that's all outside, right? Anything inside the square root, even if it's in front of the x, right? Anything around here, that would be inside the function because it's inside the square root. That's kind of like the easier one to see. Same thing for absolute value, right? Absolute value, kind of easier to see because here and here is outside, right? That's outside. Obviously anything here and here, that's inside. Easier to see. What's not as easy to see, maybe, I don't know, would be maybe something like x cubed, right? So if I'm talking about the x cubed function and I'm talking about outside versus inside the x cubed function, what am I exactly talking about? Well, for that, I'm talking about outside is, again, a little bit more straightforward. It would be anything here or out here, right? That's outside. But for inside, inside means I have to be inside the cubed part of the function. So that means before I cube it, and essentially what we would have to do is we would have to put parentheses, right? Because now we know that x cubed is the same as parentheses x cubed, right? But anything inside here is now an inside transformation. So that's being inside the function, sort of. So when we say inside, we mean inside the function, like before doing the function, right? So before taking the square root, before taking the absolute value, before cubing the function, right? That's inside. Okay. Outside means after you've done the square root or the absolute value or the cubed, in that sort of like order of operations type way of thinking. So hopefully I didn't confuse you. Hopefully you guys understand what I'm talking about now when I say inside and outside the function. So let's take a look at some practice problems. I would ask you to go ahead and try to identify the transformations. If you can kind of try and remember back to what we were talking about before, try to write it out. Maybe go back, check this, okay, and write your answers here, and I will continue and do the same. So for part A, I see a +5 and it's on the outside, so this is a shift up. Here I see multiplying by 5 and adding 6. Both of them are on the outside because I don't see any parentheses here. So, and we're talking about an x cubed function. So this is a vertical stretch by a factor of 5 and a shift up 6. I should probably specify, right, how much we're doing these things by. Here is the cube root function, and we see that there's a -2 on the inside of that cube root function, and so that's going to be a shift to the right 2 units. And the next one, we see a +1 on the inside, a -4 on the outside of the absolute value, and so we have a shift to the left 1 unit and a shift down 4 units. Okay, let's see what these transformations do graphically. So what we have here is we have the absolute value function. One thing to keep in mind on this graph, check the scale. Each of these boxes, each of these marks is 1/2 unit. Okay. And what we're going to do is we are going to first describe these transformations here, questions 3 through 7, or 1 through 5, 3 through 7. And then we're going to graph those and we're going to label them. So first, go ahead and write down what those transformations are, just like we did on the previous page. And then I'll kind of show you how we're going to go ahead and graph those. All right, so this first one is a shift up 3/2. Next one is a reflection over the x-axis. This one's going to be a vertical stretch by a factor of 2. Just simplify that by 2. And this is a vertical compression by 1/3. And here we're going to shift down 3 units. Okay, so those are the transformations. What do they look like graphically, though? So for number three, A of x, let's talk about A of x. shifting up 3/2. So it's essentially shifting my whole function up 1.5 units. So I'm going to take all of my points, all of my original points on this graph, and I'm going to shift them up 1.5 units. So I'm going to take this point and it's going to go up 1.5 units. So it's going to go up to 1.5. Right, and I can see that that's going to be shifting them all up basically 3/2, right? So each of these boxes are halves. So I'm going to take not every single point. I'm going to take maybe the major points and shift them all up 1.5 units. And what I get is this. And so now I can graph this. And label it A of x. So what we see here is it's the original function and it's just been moved up 1.5 units. Okay? For B of x, we're going to reflect this over the x-axis. So what I'm going to do is I'm going to take these points that I see on the original function, I'm going to see how far are they from the x-axis, and I'm going to do that same distance on the other side of the x-axis. Okay, so here I'm going to see that it's 6 units above, so I'm going to have to move it 6 units below. Right, and this one as well, 4 above goes to 4 below, 2 above goes to 2 below. A point on the x-axis reflected over the x-axis stays on the x-axis. And then I'm going to continue doing that for all of these points, sort of reflecting them over the x-axis. And I get this, which looks like the original function reflected over the x-axis. And that didn't come out very good, but close enough. Let's label that B of x and move on to C of x. This is going to be a vertical stretch by 2. So what I'm doing here is I'm multiplying all of my y values by 2. Right? That's going to be how I vertically stretch that. So what we see here, and it's going to start getting a little confusing, so let's see if I can change colors. Let's go to red. Okay. So for C of x, I'm going to multiply by 2. So this y value of 0 multiplied by 2 stays at 0. Okay? But a y value of 1 multiplied by 2, that goes up to 2. Right? A y value of 2 would go up to 4. A y value of 3 goes up to 6. And the same thing on the other side, right? This gets multiplied. Y value here of 1 gets multiplied by 2. Y value of 2 times 2 is 4. A y value of 3 times 2 is 6. And we get this shape, which looks much more narrower than the original shape. That is definitely one of the words we used in Unit 1, right, to describe a vertical stretch, because we've taken that sort of V shape and we've stretched it vertically, which kind of pulls it in. Okay, and that is, what is that, C of x. Okay, now d of x is, we're going to vertically compress it by 1/3. So essentially we're going to multiply everything by 1/3. Multiplying by 1/3 is the same as dividing by 3. So let's multiply all our y values by 1/3. And I'm going to do the ones that are easy for me. So 6 divided by 3 is 2, right? So that comes down to 2. This y value here of 3 will go down to 1. 0 will stay at 0. And again, 3, where's 3? There's 3, goes down to 1. And 6 goes down to 2. And we get this V shape that looks like it's been vertically compressed or squished, right? And much more flattened out, it's much more wider. Okay, and that is d of x. Next one is going to be a shift down 3. So I'm just going to, just like the first one, shifting up 3 halves, I'm just going to subtract 3 from all of my y values. And I'm going to, let's go ahead and, whoops. Okay. Okay. So take all of these y values and just subtract 3. So 0 goes down to -3. And this 2 goes down to -1. And so on. 4 goes down to +1. 6 goes to 3. And same thing on the other side. And I get this function that looks like it's the same shape as the original, right? We have preserved its shape, but we have just moved it down 3 units. All right, so there we go. That's what transformations look visually. All right. Number 8, let's write these functions using the given transformation. So a translation also means shift, right? So translation to the right 5 units. We are working with this function, f of x equals x squared. Let's go back to blue, it's easier to see. And so remember, for inside and whatnot, we're going to need a parentheses. So translation to the right 5 units means I'm going to be subtracting 5 inside the function. And so this would be the new function, right? X minus 5 squared. If we're going to go down 3 units, it's going to be x squared minus 3. Okay? Go ahead and try the rest, and then check with me after you've done it. So a vertical scaling, a vertical stretch by a factor of 5 means I have y equals 5x squared. And then to the left 4 units, y equals x plus 4 squared. So I got that inside the squared function. And a factor of 1/3 vertically, 1/3 x squared. Okay. Continue trying number 9. This time we're using the absolute value function, and there may be more than one transformation. So go ahead and try these 4, and then unpause when you're ready to check. So 2 units left and 4 units down means I would have, so 2 units left means x plus 2 inside. 4 units down means minus 4 on the outside. So that's what we would get there. 2.5 units right and 1 unit up. So to the right means minus 2.5 and 1 unit up. So that's what we get from B. And then scaled vertically by 1/2. And then to the right, 3 units. It's 1/2 x minus 3. 1/2 absolute value of x minus 3. And then 5 units right of vertical scaling by reflecting across the x-axis with a vertical scale factor of -2. Okay, so -2 is on the outside, being multiplied, my coefficient essentially, and then 5 units to the right means x minus 5, and that's what we should have there. Number 10. Number 10 is a Regents type question, something we probably see on a Regents exam, and again, it goes back to this idea when we graphed all of this stuff. What did we do? We took individual points and we moved them, right? We took individual points and we applied the transformation. That's all we're going to do on this question, right? So number 10 says the vertex of a quadratic function, f of x equals x squared, is at 0, 0. It's giving the coordinates of a point, which happens to be the minimum of the graph. Okay, based on your work, where do we predict the vertex will be for this new function that's the same function, but it's been shifted? How has it been shifted? It's been shifted to the right 2 units. Well, that just means we're going to take this point and shift it to the right 2 units. And if we think about that, a point at 0, 0 being shifted to the right 2 units is going to make the coordinates of that. What's the coordinates of this new point? 2, 0. And I kind of like to do this visually because it just makes sense to me. And so the answer to this would be 2, 0. That would be the new vertex. Right? Hopefully? Yes. Question 11. We're going to match the correct equation and description of the function with the given graphs. So we have 4 different graphs: f of x, g of x, h of x, p of x. And we have 4 different equations, 4 different descriptions. Okay, let's take a look at the first graph, f of x. So I see this graph is opening down, first of all. So I know that the number in front has to be negative. And I also look at the rest of the graphs and notice that none of them open down. So this one could probably be a little easy because now I can just find that negative out front and know that it's the only one that opens down. So that means that equation is E3. Description. Let's see a description. So the graph of the parent function is translated down 3 units and left 2. Down 3 and left 2 doesn't look right. The graph of the function does not have x-intercepts. Does this graph cross the x-axis? No, it doesn't, which means it does not have x-intercepts. So that's the correct description, D2. So we use that, and we use that. Okay. G of x looks like a regular parabola, but maybe it's been shifted to the right 3 units. So let's take a look at our options here. And this one looks like it has 2 different transformations, This one looks like it's been shifted to the right 3 units. E1. Okay. Description, let's see. Down 3, left 2. No. Coordinates of the y-intercept is 0, 1, and both x-intercepts are positive. Y-intercept is 0, 1. Yeah, that's correct. Both x-intercepts are positive. Yeah, both of those x values are positive. That's correct. So that... Oh, wait. My bad. I just jumped down to the wrong graph. Okay, well... Okay. The graph of the function only has 1 x-intercept. Yes, for the correct one that I was supposed to be working on, this only has 1 x-intercept right there. So there's our description, D4. Use that. Next one, h of x, somehow I have a feeling it's going to be description D3. And the equation looks like the vertex of the parabola, which is, remember, when I just graph x squared, the vertex of that parabola is right at the origin. So it looks like it's been shifted to the right and down, right 2, down 3. And so I have to find the correct equation. Which of these equations, E2 or E4, is right 2 and down 3? If you said it's E4, that would be correct, because minus inside means right. And our description is done. Last one, let's double check to make sure what we have remaining makes sense. So that's left 2, down 3. Left 2, down 3 looks good. That's E2. And description, left 2, down 3. Okay, that's good. D1. So there's transformations again, but hopefully now, after a lot more work in algebra, the transformations are making a little bit more sense. And yeah, that's it for me. I'll see you in the next one.